right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another installment of Math 212. Hopefully the quiz wasn't too bad. Yeah, some of you might have been a little bit annoyed with the bonus problems, as I can tell, but yeah, it's extra. We'll be talking about some of them today. Well, there's something in the bonus problems that we won't be getting to today, but it wasn't the answer anyway, so it's fine. By the end of today, you should be able to answer all the bonus problems. So let's actually just jump into it. Since we already took the time out for the quiz, let's not waste too much more time. And here we go. So this is what we were doing last time. This is the last half of the last class where we started to introduce vectors. A vector is just a quantity with magnitude and direction. We saw that we can represent them by a directed line segment. The magnitude is the length of the vector, and the initial point or the tail is called is one starting point, and you can move in some direction to some other point called a terminal point. We can name vectors. Usually you put a little arrow over it when we want to talk about vectors. We also learned that vectors are considered equal as long as they have the same magnitude and direction. However, every now and then we'd want to think of a vector as starting at the origin, and we call those guys position vectors. We learned about that as well. We can write vectors similar to how we write coordinates, and the coordinates will tell us that if it were a position vector, then the actual coordinate A1, A2 would be where the head of or the terminal point of the vector would end. You can also think of the coordinates as telling you how far left or right you move and how far up and down you move in the 2D case. In the 3D case, this is a little bit more complicated, but hopefully that was intuitive. We drew a vector in 3 space, same idea using the rectangular coordinates. We saw that. We saw how to create a vector that's connecting 2 points. Essentially, you do the final minus initial idea. And we looked at the magnitude of a vector. This is just using the distance formula applied to vectors, and we saw that that's how we could do it. What else did we see? We looked at operations on vectors. We can add 2 vectors together. We can actually find scalar multiples of a vector. We looked at what adding the vectors would mean. You needed to know this for the quiz today. What direction is A plus B? If you know A and B, what direction is A minus B? If you know that. Taking the negative of a vector means changing its direction. And finding a scalar multiple of a vector, you can actually stretch the length of the vector by that scalar multiple. So we saw that. Then there were some properties that we just kind of listed here. We didn't really go through them, but they're essentially kind of obvious, very natural. So nothing really strange here. Most people reading this list would kind of be convinced that these things are true, so we're not going to really talk about them. What we are going to do is we are going to get through some examples very quickly. So you never had to actually compute any of this stuff in the quiz today, but you did have to know geometrically what these guys would have meant. That being said, let's actually jump into it, do some computations. Nothing crazy. We're just going to compute based on these vectors given A and B. A is the vector 1, 2, 3. B is the vector -4, 0, 5. If that is the case, what is the magnitude of B? Of A, sorry. So, I mean, there's not much to actually say here. So this is just going to be the square root of the square of the sum of the components. So this was a formula that we had last time, just to wrap up here. So you put the first component here, put the second component here, put the third component here, and that's essentially it, actually. So that's going to be 9 plus 4 plus 1. So that's 9 plus 5, that's 14. So that's the magnitude of this vector. Magnitude of A is radical 14. Nothing too crazy there. Now, if we go to A and B, again, we know that A and B, let me copy these guys here. Okay, so if A and B is that guy, what is A plus B look like component-wise? Since these guys aren't so bad, I might let you guys just do it for me. So I had 1, 2, 3 plus minus 4, 0, 5. What is that? No, something is off there. Right, so minus 3. So I'm not sure if you meant that SQ there because it shouldn't really be an SQ. Okay, so yeah, you add corresponding components. So we don't need to write this line down, but essentially what you're doing is you just take this, add the first two components, add the second two corresponding components, add the third pair of corresponding components. You don't need to write that. You can just jump to, this is minus 3, comma 2, comma 8. That's that one. Okay, moving A and B down here and moving this guy. Subtraction, very similar. You just subtract the corresponding components. So this is going to be 1, 2, 3 minus 4, 0, 5. And this would be, of course, you subtract the corresponding components. 1, that should really be an angled bracket. 1 minus a minus 4, 2 minus 0, 3 minus 5. That'll give you 5, comma 2, comma minus 2. Okay, not so bad. Hopefully not too bad.
I have a quick question with subtraction of vectors.
Yes.
So when you're subtracting vectors, should you always do v1 minus v2, or is it v2 minus v1?
Oh, you do it in the order. So it's going to be the component of this minus the component of that.
Okay, got it. Thank you.
Right. So the thing where you do final minus initial, you have to remember that comes in when you have like you're going between 2 points. Right? So if I'm going from A and I'm ending at B and I wanted to actually find that vector, where the final minus initial comes in is when I'm finding the components of that vector. So you don't really want to think of it as subtracting 2 vectors. You're actually subtracting the final coordinates from the initial coordinates. So if this one was, this is not a vector. If this is the coordinate B1, B2, B3, and this is the coordinate A1, A2, A3. Then to find the vector that goes from A to B, it's going to be B1 minus B2 and undo. B1 minus A1, B2 minus A2, and B3 minus A3. So when you subtract things in the reverse order, that's the context in which you do it. But if you're actually writing down a subtraction of vectors, you write the subtraction in the order that is given.
Got it. Thank you.
Okay. Okay, 2a. So this is just 2 times 1, 2, 3. And you just multiply corresponding components by 2. Right? This actually keeps the same direction as A, but it stretches the vector to be twice the length that it was before. If it were a minus 2, it would literally flip it in the opposite direction. So that's that. E. (3b), similar kind of idea here. So this is going to be 3 times minus 4, 0, 5, minus 12, 0, 15. There we go. So hopefully nothing too crazy here. We're doing the operations that you kind of do it component-wise. And you don't do anything too crazy component-wise. Yes, minus 2a would have the same magnitude as 2a. It's just in the literally the opposite direction. They're still technically what we would call parallel, quote unquote, but the arrowheads would point in the completely opposite direction. Yeah. So we drew some of those last time. Yeah. So if this is a, 2a is same direction. So whatever angle it's pointing at in space is going to be the same. It's just stretched by a length of 2. If I do minus 2a, it just literally flips the arrow around in the opposite direction. Okay, and here, this is 2 times a, 1, 2, 3, minus 3 times b, minus 4, 0, 5. We actually computed each of these individually, but you can compute them again on the spot. 2, 4, 6, minus 12, 0, 15. So that's going to be 2 minus a minus 12, 4 minus 0, and 6 minus 15. And there we go. All right, nothing too crazy there. Those were just all the computational examples we had here. So not super interesting or complicated, but very important that you know how to do those. Let's move down. Next thing I want to introduce is some new notation. Let's get these guys out the way. We do have some interesting stuff to talk about today, but we're not quite there yet. We're still kind of learning what vectors are and notations and how to write them down and how to do just some basic mathematics with them. But we're actually going to use them to build up some important conceptual ideas today. Okay. All right, so let's talk about the standard basis vectors and another notation for vectors. And with the warning, do not mix up the notations. Okay, so in n space, so this is Euclidean n space. If you think of n-dimensional space in the same way, like in rectangular coordinates, whatever that might mean, we denote some vectors, these guys, e sub i's. These guys are called the standard basis vectors. So this is a kind of vector that has zeros in all components, but it only has a 1 in one of the components in the ith component, right? So I can talk about in, let's say we're in R5, right? I can talk about the vector E2 in R5. Well, that's just a 5-dimensional vector where there's a 1 in the second position and zeros everywhere else. Or I can talk about E5 in R5. So that's 1, 2, 3, 4, 5, etc. Okay, so these guys are called standard basis vectors. We'll see what those guys are in a little bit. Well, not fully, but we're going to kind of see how we can actually build these guys up and why we can call them basis vectors. Okay, but that's how we kind of name them. In R2 and R3, we actually give these guys names. We call them I hat, J hat in R2, or I hat, J hat, K hat in R3. So these are the guys. So this guy would represent E1 in R2. This guy would represent E2 in R2. This guy would represent E1, E2, and E3 in R3, respectively. Okay. Now we call them I, J, K. And geometrically, what are these guys? Geometrically, here's what these guys are and why we call them basis vectors. It's because they are based on the set of axes that we learned how to draw last time. And we can kind of build up any vectors based on these guys. Okay, so the I vector is the vector that runs in the x direction. So if you think of it as a position vector, it starts from the origin and runs along the x-axis, and it has length 1 running along the x-axis. So this is called the I vector. Then you could also have what's called the J vector. That guy runs along the y-axis. Again, he has length 1 and we call him J. Then lastly, we have the K vector, so-called K vector. That's the guy that runs along the z-axis. It's called K. He also has length 1. So these are all guys that are called quote unquote unit vectors. So that was something that I asked about in the quiz today. A unit vector is just a vector with magnitude 1, right? So these guys, the I, J, K, and in general, the standard basis vectors, but you really only need to know about I, J, and K for this class. These guys are unit vectors that are literally running along axes in your n-dimensional space. So for 3D space, there are 3 of them. For 2D space, there are 2 of them. For ND space, there are n of them. And they're just unit vectors, vectors of length 1 that run along the axes. And they can be used as a basis in the sense that, did I put the notes here? We can actually talk about every vector in the space in terms of these vectors. And it's a set of vectors that we can use to describe every vector in the space in an optimal way, in the sense that any smaller set of vectors wouldn't be able to do it, and any larger set of vectors would be redundant. You would have people in there that don't need to be in there. And so that's more of a linear algebra concept. You don't really need to understand the basis vectors, but that's essentially what they are. Basis vectors, it's just a vector, the smallest set that spans the space, quote unquote. Notation-wise, this leads to something that we call the IJK notation. How does this lead to IJK notation? So let's say I'm given some random vector, given a vector A, let's say its components are A1, A2, A3, right? I can write this down as, based on what we know about vector addition and scalar multiplication, this is A1 times that, plus A2 times that, plus A3 times that. So you'll notice that I'm able to take any vector and kind of expand it and set it into 3 separate parts, right? So I mean, I can do this even a little bit nicer. Just do one more step so you can see what I just did. I can split this into 3 vectors where I only focus on the part in the x component, which we spoke about what the x component is, the part in the y component, and the part in the z component. Then I can factor out those constants and be left with this. And you'll notice that I would have the I vector here, the j vector there, and the k vector here. So this leads us to the IJK notation. So for example, I could say, oh, here's the vector -1, comma 2, comma 3. And I can write that as -I plus 2j plus 3k. Or I can talk about the vector 2, 0, -4. And I could write this as 2i minus 4k. Now, one thing that I mentioned earlier is that you do not want to mix up these notations. So do not mix the notations. So either you're going to write IJK notation or you're going to write the component notation, one or the other, right? So if you wrote something like 2i, comma, 0j, comma, minus 4k, like, what are you doing, right? Or you're right, like 2i plus 0j minus 4k, and you put them in square brackets, like, what are you doing? Wake up. Right, so you wouldn't mix the notations. Either you put the angled brackets or you put the ijk. You do not do both, okay? Because, you know, that might lead to tensors and all sorts of other mathematical objects, which we don't want to study. Anyway, that's how you'd represent vectors in ijk notation. So that's just another thing that you should be aware of. So one thing you should be able to do is you should be able to recognize when a vector and what that vector means, what direction it's pointing in, whether it's written in component notation or ijk notation. You should be able to recognize these guys. All right, what else did I want to tell you about? Unit vectors. Another important definition here. A unit vector is simply a vector with length 1. That's it. It's nothing more complicated than that. It's very convenient to use unit vectors to describe directions in which we don't want the magnitude of the vector to have any influence over anything that's in our calculation. So a lot of times we'll describe a direction in terms of a unit vector, because normally sometimes we're going to want to take this direction and like multiply it by something or use it in some sort of calculations, and we don't want to actually scale our calculations at the same time. So, well, I mean, not everyone would have seen vectors before, so it's possible that people didn't know what a unit vector was. Let's see. Yeah, unit circle, that's true. But that's all a unit vector is. Now, a very important thing that you will need to know is how to find a unit vector in a specific direction. So let's say you have some non-zero vector. You want to find a unit vector that's in the same direction of that vector. You can do that by taking the vector and dividing by its magnitude. So for example, here's a problem that you should know how to solve because it can come up in various contexts. Find two unit vectors that are parallel to this guy. So I want them essentially in the same direction as A, or in the complete opposite direction of A, but I want their magnitude to be 1. How can you accomplish that? Well, the first thing you would do is you would actually find the magnitude of A, which we saw how to do last time. So it's 2 squared plus minus 1 squared plus 3 squared. And that's going to be radical 14. Okay. And then all you do is, so you have a vector u. One of the unit vectors is just going to be this vector divided by radical 14. Well, this is actually just the same as taking each component and dividing by radical 14. They're both the same. They're both the answers. So that's an answer, or that's an answer. Okay. So that's one unit vector. The other is just a negative. Oh, what just happened? The other is just a negative. So the second unit vector is just going to be negative 2 over radical 14, comma 1 over radical 14, comma negative 3 over radical 14. And those are the two unit vectors. You do this or that or that. And those are unit vectors. Nothing else to really talk about. There's literally no catch with vectors. Yeah, there's no catch. I don't know what to tell you. That being said, these are straight up definitions. So That's not even true. I feel like there are more catches in physics than there is in math. Like physics is the word problems can get really complicated. But that's it. Next one, if you're given a vector and you want to find a unit vector in the same direction, just take that vector, divide by its magnitude. So in this case, if A was the vector, so here, you'll notice that I have like this vector here, boom. Call that the vector A, and its magnitude is, I don't want to put that in. And its magnitude is radical 14, and this is the vector A. Then essentially what we just found is we found a unit vector in the same direction. This has length 1. That's what I called U1. And then I found another unit vector in the other direction, which is still parallel. So it goes exactly the opposite direction. It also has length 1. That was U2. So that's it.
I have a quick question. If you want
Yes.
to find more parallel vectors, would you just multiply it by a scalar?
Yeah, parallel by definition. I believe I had that before. Yeah, two vectors are parallel if they're scalar multiples of each other. So any scalar multiple. So
Okay, got it.
for example, for this problem, I specifically asked for a unit vector. So that's technically a scalar multiple. I could think of this u1 as 1 over 4 radical 14 times the original vector. So these guys are scalar multiples, but they're scalar multiples that have length 1. Yeah.
Okay, got it.
Okay. You guys are your trust issues. And that's basically it. So now that's vectors. We looked at the definitions and some basic things that we can do with them. That's kind of it. Like, very intro to vectors, very nice. Not a big problem. Okay, so now let's talk about trust issues. Now let's actually get to the things that we're going to actually want to use vectors to do. Okay, so that's leading us into the next section, where we are going to talk about the dot product. And let's make this a little bigger. Okay, so it's going to be our next section. This is section 12.3, the dot product. We're going to talk about that guy. Now, the dot product happens to be, and here's what Kayla's mad at again. The dot product happens to be one of the answers to the problems on the quiz, one of the bonus problems. Okay, so if you didn't know that, here's how it's going to happen. But I don't want to just jump into the dot product and talk about, oh, this is a dot product. Here's the definition. Everyone does that. I'm actually going to want to motivate where the dot product would come from, and also I'm going to provide a lot of the motivation for where the cross product would come from. Why would we care? Why would we create something like this? It's called a dot product. So before last class, we spoke about addition of vectors and scalar multiplication of vectors, and I mentioned that there's no real way to multiply two vectors in the sense that you would think of multiplying two numbers. There's no division of vectors or anything of that sort. But there are things that we call vector products, where we can take two vectors and we can use those vectors to create some other object. The dot product is creating a scalar object given two vectors of the same dimension. And I'm going to talk about where that comes from, why we would even care. So that's what we're going into. But first, to talk about the motivation behind such a thing, we're going to talk about patches, directions, and normal vectors. Okay. So what you saw last time is that 3 dimensions was already a little bit different. It was a little bit weird compared to 2 dimensions. And we saw that there were things that we believed in 2 dimensions, which when you extend things to 3 dimensions, it wasn't quite the case. It wasn't enough. There was info being left out. For example, we looked at the equation x equals 1. As far as a 2-dimensional person is concerned, that's a line. However, we saw that it was actually a cylinder. And if we saw x squared plus y squared equals 1, in 2 dimensions, we thought of that as a circle. but we also saw it was a circular cylinder, right? X equals 1 is a plane. It's also technically a cylinder, but whatever, we would call it a plane. X squared plus y squared equals 1 is a circular cylinder. So there were these equations that we can write down in 2D, but then when we go to the 3D world, those equations don't make sense. The language doesn't make sense anymore. So that's an issue. It turns out that the better way to describe curves and objects in space in higher than 2 dimensions is using vectors. And we're going to talk about vector curves and vector surfaces in the next class. But in order to prepare you for that, we're going to need to talk about some other things first. But that's a better way to describe things. So rather than saying, oh, this is the equation for this thing, it's nicer to say, okay, this object that I'm going to define is going to be defined in terms of the things that are at the tip of this vector that it can trace out a curve. So I can use a bunch of vectors to trace out a curve or a surface, and that's how we want to define them. And this leads to reimagining our space in a whole different kind of light, right? So for example, we are going to want to be able to sketch things. We're going to want to be able to actually do mathematics and do calculus in higher dimensions. And then so you might have to start asking the question, well, all right, if we're going to do calculus in higher dimensions, what would we need to be able to do in order to do calculus in higher dimensions? Well, what were the main things we had to do in calculus? Well, yes, there were limits, but why do we care about limits? Well, we use them to develop the derivative and the integral. Those were the main guys in calculus, right? What is a derivative? Well, it's a measure of slope, right? And what was slope? Well, it's kind of was the direction in which a curve was moving, right? And so that's what we need to be able to measure. We need to be able to measure direction in which a curve is moving. And how are we going to do that? How are we going to talk about direction in which something is moving in space, right? That's one issue. Another issue is, remember when we're doing integration, right? Integration was, how do we develop that? Well, we had some function that we wanted to find the area of. We dissected the input space, which for us was just the x-axis, into subintervals, right? And we wanted to find the area under a curve under this interval. So we took that interval, we dissected it into a bunch of subintervals, and what we did is we drew rectangles on that interval, right? So we needed to be able to dissect our input space, and then at the same time, measure the magnitude of these dissections. From that, we can take the magnitude of the dissection times the output of the function, and that gave us the area of the rectangle. We can add up all these guys to find the area under the curve, and we could approximate it by taking more dissections, okay? So we're going to want to do the same thing. How are we going to find the magnitude of these dissections? How are we going to find the direction in which they're moving, right? Now, in 3 space, we're going to be looking at objects like this guy, right? So here's an example of something that we'd see in 3 space. This is some random function. We're going to look at surfaces like this. This is what's called a surface in 3 space. And a lot of times, we will describe this as an equation as well. There's a way to describe this as an equation. It will be something like, oh, z equals some f of xy. In other words, my x and y are the inputs, and z is the output, right? And this is a common way to represent a surface. It's not the only way, and sometimes it's problematic, but it's a common way to represent a surface. And so now you might start talking about, well, how can I talk about all the things that I could have talked about in 2 space, and how can I represent this input? Well, remember how in the case of integration, when we wanted to find the area under a curve, we found the interval that we wanted to find it over, and that was some measure of some piece of our input space that we could dissect. It turns out in this case, our input space is in the xy plane. So I could have a coordinate x comma y in the xy plane. I plug it into my function, it's going to output some value, some z coordinate, z. And so that's one point. And I can plug in a bunch of points and do this for a bunch of different points. And they will all give me z values. And then I'll be able to actually plot out all these points in space and create something. What you'll notice here is my input space now is going to be some region in the xy plane, right? There's going to now it's not just an interval. It's going to be like a two-dimensional region is what my input space is going to look like, right? Now, when I want to actually talk about integration or something like that, what I'm going to have to do is I'm going to have to be able to dissect my input space, right? I'm going to have to be able to slice it up. And so here, what you'll notice is there's like a region of input here that you can actually see projecting up to some other patch here that's along this surface, right? And so now I want to be able to talk about, well, if I want to do integration, for example, I'm going to have to, instead of erecting rectangles, I'm going to have to erect boxes. I'm going to talk about the area of the input space and all that good stuff, right? And then I'm going to have to talk about the area of these patches to describe this actual surface and the slant that these patches are in space. These are going to be very important things for us to be able to figure out, okay? So now, how do you actually go about figuring things out like that, right? So that's where our motivation is going to come from. So we are in 3 space. Things already work differently from 2 space. We want to be able to do the same things that we could have done in 2 space. This will mean, oh, I need to be able to find the area of dissections of my input space. I'll need to find the direction in which these input patches are actually lined up. So I can dissect the surface into patches, and then I need to be able to talk about the area of these patches, the direction that these patches are slanted in. So how do you actually go about doing that? Well, let's say I took one of these patches, right? Here's a patch that I took from up here. Let's say I just took one of these yellow patches, and here's the guy, right? One way to talk about the patches is, one, I can talk about the vectors that line this patch, right? So I can have a vector A here and a vector B that's along the edges. And maybe what if I want to talk about, let's say I can talk about the area of this patch. Let's say we want to find the area of this patch. How can I find the area? Well, one way to find the area, so let's say we're interested in the area of this patch. My brain feels foggy today. I don't know. Didn't sleep right or something. Let's suppose we care about the area of this patch. How would we actually go about figuring out what that area is? And let's say for some reason I know the angle, if we knew the angle. Now I'm going to show you how to find the angle between the vectors as well. But let's say I wanted to find the area. One way you could actually find the area is to, if I took that patch, right? So here's that patch right there. And what I can do is I can actually slice it like this along a diagonal and then focus on that part, right? So I have a triangle where the magnitude here is actually, I wrote that as B earlier. And the magnitude over here is A. And then I know the angle between A and B here is theta. And so I can know the area of the patch is just going to be 2 times the area of this triangle. All right, where's my high school geometry people at? How do you find the area of a triangle when you know the length of 2 sides and an included angle? Do you guys remember how to actually do that? Do you remember? Okay, so there is a formula that says if you know an angle here and you know 2 sides here, then the area is equal to 1/2 AB sine theta. Okay, so let me just tell you that. So this here is going to be 1/2 times the magnitude of A, magnitude of B, sine theta. So it turns out that I can find the area of the patch by just AB sine theta. Now, this is something that we will come back to actually tomorrow as well. This is going to actually be important for something that we're going to do tomorrow. But that's how we can find the area of a patch, right? Find two vectors that run along the edges of the patch. Take the magnitude of one times the magnitude of the other times sine of the angle in between them, and it actually gives you the area of the patch, right? So that's that formula here. So that's a formula that we would have known from high school geometry. Okay. Now, let's say, how would we actually go about finding the angle, right? So let's say I don't know the angle. So let's find the angle. So again, I have a vector here, B, and I have a vector here, A. All right, let's see who was also paying attention to last week's class. And this would have helped in the quiz as well. What is the black vector? In terms of A and B, what is the black vector? It is not A plus B. Right, like A plus B is if I went along A and then I added B, A plus B would be the vector that goes over here, right, along the the angle of a parallelogram. It's actually A minus B. So that's actually the angle here. So what is the vector on the other side? This is A minus B. Just had that filled in. Okay, so now we have a triangle. Let's call this guy C. So I have a triangle. I know the angle. There's an angle here that I care about. I know the magnitude of this length here, which is a B. I know the magnitude of this length here, which is an A. I know the magnitude of this length here, which is a C. Can you tell me how to find the angle? How do you find the angle in this case? That's right, law of cosines. Yes, we all remember law of cosines. Okay, so that's another thing. So whenever you have three sides and you want to find an interior angle, you can actually use the law of cosines. Now, of course, we all remember what the law of cosines is, but just in case I posted it here. So here's what the law of cosines actually says, right? Now, there are three different versions of the law of cosines. They're all the same thing, but it just depends on what side length you actually care about or what angle you actually care about. So in our example, we actually care about the angle that would be labeled C. And so I can actually use this equation right here to talk about C. So in other words, if I have a triangle where this has magnitude A, that has magnitude B, that has magnitude C, then it automatically applies by the law of cosines, where my C is A minus B, of course. A minus B forms the other side of a triangle, whereas A plus B is the diagonal of the parallelogram formed by the angles, right? So geometrically, you guys need to remember that. If I take A minus B squared, that should give me A squared, magnitude of A squared, magnitude of B squared, minus 2 magnitude of A, magnitude of B, cosine theta. And we can use this. This equation is important. We're actually going to come back to it later. This equation is important. So finding the angle theta is important for being able to find the area of our patch, but finding the angle in the first place, we can use law of cosines. From this, we can use law of cosines to say that the cosine of theta is going to be, magnitude of A squared plus magnitude of B squared minus magnitude of A minus B squared all over 2 times magnitude of A magnitude of B. And then we can take the cosine inverse of all that to find the angle. Okay, so we'll actually come back to that in this section, but that's how we're going to do it. So remember when you were back in high school and you're like, what are we going to need all this for? Yeah, well, now we're actually seeing how we're needing it. We needed it for world building. We needed to figure out how to actually move around and actually do things in higher dimensions. Okay, well, one of many reasons why we need it. These basic geometric formulas are actually useful for tons of reasons. Okay, all right. Now let's talk about direction. Okay, so we saw that areas of patches are important to be able to figure out. I can find the area using this little known trick from algebra class or geometry class back in high school. I can find the angle, because to find the area, I'll need to know how to talk about the angles. I can find the angles using the law of cosines, which we did here. Now let's talk about directions. Directions are going to actually be very important as well. So let's say I'm in 3 space. And I have a little patch right here. And I care about actually finding the direction of this patch. So this is a patch in space. What if we wanted to find to measure how this patch is, let's use the word tilted. Okay, so I want some sort of directional way to talk about this patch, right? So this is like that same yellow patch that we had, right? So it's floating in space. I wanted a way to talk about at what angle or direction or some way to describe how it's actually floating in space, right? So I want to be able to describe this in some way that's kind of analogous to what the derivative or the slope would have done for us back in 2 space, right? Talk about how it's going to be slanted. Any ideas on how we can actually figure out how something is going to be slanted?
Do we use a dot product?
How? How would you use the dot product?
Because if something's slanted, then that would have to mean 2 sides are parallel. So you would use a dot product to find if the 2 vectors are parallel.
Well, they don't have to be parallel, but suppose you could find a vector running along here, call that A, and I could find another vector running along here, call that B. I mean, how would the dot product of those guys, and I mean, we haven't even spoken about what a dot product is yet, but how would the dot product of those guys help?
Oh, because we can see if it's orthogonal, because if the dot product is 0, that means that's orthogonal, so that means that's perpendicular.
Yeah,
Or
but
is that the cross
does these
product?
guys have to be orthogonal? I mean, if your patch wasn't, what if it was like a parallelogram? Like, would that have made a difference if it was like slanted, cut in a weird way? Now all bets are off. How can you describe the direction in which this patch is slanted?
I'm not sure. I'm just gonna let you teach.
So vectors is how we normally would describe direction, right? Can you tell me a vector that can describe how this patch is slanted? So now the typical first guess, which is not necessarily correct, the typical first guess to talk about this one is to use a vector parallel to the patch. However, it turns out that this does not work. And how can you actually see that this does not work? So, I mean, it's three space. So maybe it's nicer if I showed you guys. So let me actually show you how this would look. Okay. So let's focus on me for right now with this book. Really nice book. I like this book anyway. Okay. So here's a patch. It's slanted in space somehow. I want to talk about a description of how it's slanted in space, right? So you might think, okay, let's talk about a direction. Well, we learned about vectors last class. So let's use a vector to describe the direction which is slanted. And so you say, okay, what vector are we going to pick? Well, I can put a vector. It's parallel, right? Now, it turns out that that is not actually great. And the reason why, as you can see, is that I can take that vector, which is also parallel, and it points in a completely different direction than the first vector that I had tried, right? So I have two completely different directions that are parallel. In fact, in this little box, there's an infinite number of directions that are parallel to this patch, right? Which means if I decide to say, okay, I'm taking this vector that's parallel to this patch, and that's how I'm going to describe the direction, then it turns out a million different people could come up with a million different parallel directions that are also parallel to the patch. And all our directions would look completely different. No one would be able to agree on anything. And we'd all be like, it's pointing in this direction. No, it's pointing in this direction. No, it's pointing in this direction. Because there's an infinite number of directions that you would have that are parallel to the patch. So it's not actually good enough to find something that's parallel to a patch to talk about its direction. So now you would be able to say, well, okay, so if I can't pick something that's parallel, maybe pick something that's not parallel. So maybe some vector that's poking out of my patch is going to describe the direction in which it's slanting. And so now I'm going to talk about, well, what kind of vector could I use that is going to be poking out of my patch in such a way that it can uniquely describe its direction. I can use this vector to describe the direction. Everyone's going to agree, okay, that's the direction it's pointed in. I understand everything that you're saying. Would a vector poking out at 30 degrees to this thing work? And you'd quickly realize that the answer is no, because again, there's an infinite number of directions poking out at 30 degrees. And we can have a million different people giving a million different answers. So not a great way to define direction. It turns out that no matter what angle you pick for a vector that's poking out, that's supposed to describe the direction of this patch, you're going to run into the same problem, except for one angle. Anyone can guess what that angle is? $90 degrees? Okay, so 90 degrees. Okay, yeah, that's the answer. It turns out that the right angle is the right angle, right? If I have a vector at a right angle to this patch, then that actually uniquely determines the direction of the patch. If I wanted to describe the direction at which this thing is floating in space, all I need to do is tell someone this vector is perpendicular to this patch. Now, the word that we use for perpendicular in higher dimensions than 2 is orthogonal. So that is a phrase that you saw in the quiz today. Orthogonal really just means perpendicular, but it's a higher dimension of perpendicular, right? Because I'll tell you about it. Maybe I'll do that right now. So in 2 space, perpendicular is very well understood. If I have something here and I ask you, what is perpendicular to this in 2 space? Well, it's that guy, right? Or you can pick the other guy that goes in the other direction, but it's like negative reciprocal of the slope, right? It turns out in 3 space though, if these guys are floating around in 3 space, that's no longer true. See, that's perpendicular, but so is that, so is that, so is that, so is that. There's an infinite number of things that are perpendicular, right? So it turns out once you go to higher dimensions, perpendicular takes on a whole new meaning. It's a lot more comprehensive than perpendicular meant in 2 dimensions. So we gave it a whole other name, right? So we call it orthogonal, right? So we say something's orthogonal, meaning it meets at pi over 2 radians or 90 degrees. but it can do so actually in an infinite number of ways once you're in higher than 2 dimensions. So that was an issue. So, however, once I have a direction that's perpendicular, now remember, the position of a vector doesn't actually matter. If someone tells me this vector over here, these vectors are all going to be the same. Every perpendicular vector that someone can pick is going to be parallel to the perpendicular that I picked, vector that I picked. Even the guys that point out in the other direction here, that's going to be the case as well. So it turns out, to talk about the direction of a patch, I'll need to be able to talk about finding a direction that's orthogonal to the patch. Now, a vector that is orthogonal to something is what's called a normal vector, right? So that's another phrase. It's in the notes, so I'm just going to talk. In order to talk about the direction in which a patch is slanted in space, I can just find a normal vector to that patch. This is a vector that is orthogonal, aka perpendicular, to the patch. So now you're running to the question of, well, how would I go about finding such a vector? How can I find, given some patch, how can I find a vector that's orthogonal to it? And so now you might have the idea, well, I guess now we can use something that's parallel to the patch. Well, if I can find a vector that's parallel to this, and then I can find another vector that's orthogonal to that, then that will allow me to find a direction that's orthogonal to the patch. However, that would be a great first guess, but it's actually not good enough, because you see here, again, there are tons of ways that I can be orthogonal to a single vector. So this vector here that's in space, there are tons of ways that I can be orthogonal to that. How do I know that I'm picking the right one that's orthogonal to the patch itself? Well, it turns out, I don't have enough hands, that's right. It turns out that if you use two vectors, so here's my patch, I care about finding the direction, and I know in order to talk about the direction in some meaningful way, I need to be able to find an orthogonal direction to the patch. However, having one vector that's parallel to it is not good enough. It turns out having two vectors that are parallel but pointing in different directions is actually going to be enough, because it turns out that if I have those two vectors, let me throw this down. If I have those two vectors and I find a vector that's orthogonal to both of these vectors at the same time, then it will necessarily be orthogonal to the patch itself. Because the moment I try to be orthogonal to one but not the other, I will automatically break orthogonality with the patch itself. So once I can find two directions in the patch that are parallel, and I can find a direction that is orthogonal to both of those vectors at the same time, then that would be a way for me to find the direction of this patch, which is very important. Okay. Now it turns out that there is a way to find, given two vectors, let's say they're in 3 space, given two vectors in 3 space, there is a way that we can find a third vector that is going to be orthogonal to both of these vectors at the same time. This third vector is called a cross product. Now that's not the dot product, but I'm kind of motivating both of them at the same time here, because they kind of go hand in hand. They're different aspects of the process. You might need a dot product versus a cross product. So that's what a cross product is, and that's what we're going to do actually tomorrow. But that's something that you should actually be aware of. When we're talking about directions in 3 space, again, your intuition from 2 space will fail you, because in 2 space, you talk about direction by talking about something that's parallel to something, right? How do I know these two lines are heading in the same direction? Well, are their slopes the same? Are their slopes parallel? That's what you would think about. Same slope, we just run parallel, it takes you the direction. In 3 space, this is no longer true. Talking about direction in terms of being parallel is a bad idea. Talking about direction in 3 space requires you to talk about something being orthogonal or perpendicular. And then to be able to talk about that direction, what you need to do is you need to find two vectors that are parallel to something, and then find a vector that's perpendicular to both of those. That's what tomorrow's lecture is going to be about. How do you actually go about finding such a vector? For now, what we want to do is actually talk about, and let me actually go back to sharing the screen. And so that would have been the guess. The guess here is find a normal vector. So this is us finding a vector orthogonal to the patch. And remember, orthogonal, aka it's perpendicular. Orthogonal. Yeah, I'm really out of it today. I can't even spell orthogonal. Orthogonal equals meets at right angle. It's just perpendicular in higher dimensions, really. So that's all that it means. All right, so the same way that the derivative is a generalization of slope, but you don't just call it slope, you give it a whole new name to talk about the fact that, oh, this is a more generalized version of this concept. Well, yeah, orthogonal is the more generalized version of what it means to be perpendicular. So yeah. So we discussed some of the motivations here. To be able to actually do math or do calculus, we need to be able to talk about things like finding the area of random patches, finding the direction in space in which they slant. This comes down to we need to be able to find the angle between two vectors. We also need to be able to find a vector that's perpendicular to two other vectors, aka orthogonal. So I'm slowly going to phase out the word perpendicular and just say orthogonal. But for now, I just want you guys to remember perpendicular means orthogonal, orthogonal means perpendicular, and all that good stuff. So this is the motivation for why we want to do things. We want to be able to build up a world, be able to do calculus in this world. And it turns out we need to be able to do these things. We need to talk about directions that something's slanting. We need to be able to find the area that something's slanting. We need to measure the angle between two vectors. So now, let's actually talk about the dot product, finally, right? So let's go back to the problem of finding the angle between two vectors. Okay? All right. How would you actually go about doing this? Well, we actually saw earlier that if I took A minus B squared, we could find this. Right? By law of cosines. Okay, so we saw that earlier. Now, I'm going to illustrate what this is going to look like in 2 dimensions. You notice I have 2D vectors here. But the idea generalizes more widely to higher dimensions. Okay, but for illustration purposes, I'm just going to do 2. It'll look the same in higher dimensions, actually, but the calculations are just going to be a lot more annoying to write down. So what this would look like is, well, this is going to be the vector a1 minus b1, comma a2 minus b2, magnitude squared. This is going to be a1 comma a2, magnitude squared, plus b1 comma b2, magnitude squared, minus, well, I'm going to leave these guys just as magnitudes because I don't want to worry about the square roots. All right, so what are these guys going to look like? Well, this part is going to look like a1 minus b1 all squared plus a2 minus b2 all squared. This side is going to be, well, a1 squared plus a2 squared. This is going to be b1 squared plus b2 squared. Now remember, there's a radical here, but we're squaring them. So it's going to actually get rid of the radicals because we're squaring these guys. minus 2ab cosine theta. Now, we can solve for the cosine. And what is that going to look like? Well, it's going to be a1 squared plus a2 squared plus b1 squared plus b2 squared minus a1 minus b1 squared minus a2 minus b2 squared all over 2 magnitude of a, magnitude of b. Now I start expanding. Okay, so this is a1 squared plus a2 squared, and now you can kind of see why I don't even want to do this in general, just doing it for 2 space. But the calculations are going to look very similar. So this is going to be a1 squared. This will end up being plus 2 a1 b1 minus b1 squared. This is going to be a2 squared plus 2 a2 b2. Let me move this chat box out the way. Minus b2 squared. Now what do you notice? Things will start canceling. a1 squared cancels this a1 squared. a2 squared kills that guy. The b1 squared kills the b1 squared here. The b2 squared kills the b2 squared here. And you will notice that I have this thing ending up here. I would have a1 b1 plus a2 b2 over 2 ab magnitude. And you see this guy right here. Just put in green. See that expression, a1 b1 plus a2 b2, which you now should recognize as something that showed up on the quiz, is a very important expression when it comes to finding the angles. It turns out an expression like this will always show up. So even in higher dimensions, for n dimensions, you'll just have a1 b1 plus a2 b2 plus a3 b3 plus a4 b4 going all the way up to an bn. And so we give it a name, right? Because it's an expression, right? So people, when they like it, they put a ring on it. In mathematicians, when they like it, they give it a name. That's pretty much it. That's like, oh my God, we love this way of calculating the slope. Let's name it. Derivative. Okay, awesome, love it, right? Math people, when they like something, they name it. And so this expression here, very important expression, we give it a name. Namely, we give this expression the name dot product. So given two vectors, a1, a2, and b1, b2, the expression that looks like this, the sum of the product of corresponding components, we call that the dot product. And it works in higher dimensions as well, even though I illustrated for 2 dimensions. So if I have a vector a1, a2, all the way up to an, and b1, b2, all the way up to bn, then the expression a1, b1 plus a2, b2 plus a3, b3, all the way up to an, bn, this is called the dot product. And it is called the dot product because of the notation we use. We use a dot b. It's actually important to write the dot. Dot is importante. Okay, so that's called the dot product. Okay, so that expression, right? Now, normally people just tell you about dot product and then they give you that definition, but I wanted you to see where this guy actually came from. It came from us being concerned about finding the angle between 2 vectors. And it turns out every time you do that calculation, an expression like this shows up all the time, every time, right? So might as well, you know about that expression in the first place. Also, So you can note that because to rewrite the above, if we rewrite we would have found that your cosine of theta was, remember your cosine of theta was a1 b1 plus a2 b2 divided by magnitude of a, magnitude of b. You could actually rewrite this as now a dot b over the magnitude of a, magnitude of b. And so that actually leads us to this equation here. Now that we know what the dot product is, it's a very important expression. We can actually just solve for that expression in this equation, and we end up with this equation. So it's a very important equation that governs the dot product. The dot product of a vector a and b is going to be the magnitude of a times the magnitude of b times cosine of theta, where theta is the smallest angle between the two vectors, right? Because that's what we were searching for in the first place when we came up on this calculation. So this equation is immediately true. Other things about the dot product. The dot product is a scalar. Now, this is one of those mistakes that I see students make all the time where I don't know why they would make this mistake. They would write down a dot product and they'd write some sort of vector as the answer. A dot product is a scalar. You take the dot product of two vectors, the output is a scalar. The dot product of two vectors is this calculation. You multiply the corresponding components and you add them together. That's just going to give you a real number. It's not going to give you a vector, right? The dot product is a scalar, okay? And in fact, the dot product is sometimes referred to as the scalar product or an inner product, right? So you should just know dot product is a scalar. That's the definition. It's useful for finding the angle between two vectors. This equation with the cosine of theta is going to be the equation that you would need when you want the angle. And that's just actually a consequence of the law of cosines. So dot product is a scalar. It also has the following properties. So those are the properties right there. Here's another thing that's important, and this would have helped you in the quiz, right? So if A and B are vectors like this, they're said to be orthogonal if the angle between them is pi over 2 radians, right? So this is perpendicular in 2D. That's what I mentioned earlier. Now, if your theta is pi over 2, and I plug that into this equation that I just gave you here, that means you would get magnitude of A dot B is the magnitude of A, magnitude of B, cosine of pi over 2. But the cosine of pi over 2 is 0. And that leads us to this very important theorem or definition. A and B are orthogonal if and only if A dot B is 0. And by the way, this would mean if it's in 2 space, in 2D, this would mean that your A1, B1 plus your A2, B2 is 0. And there's your quiz answer right there. So if the dot product is 0, is the 0 scalar, that is a very important scalar in terms of the dot product. Dot products always give you a scalar. The scalar is kind of a measure of how close the angles are, how much in line they are, because the scalar would tell you what the theta is. It will suggest to you what the theta is between the guys. Right, cross product wouldn't work in either case because I just made the vectors in the quiz were 2-dimensional. Cross product only works in 3D. So that was a dead giveaway that it wasn't the cross product, right? Because it was only A1 comma A2. Yeah, cross product only works in 3D. We'll talk about that tomorrow, right? So here, the dot product is 0 is a much more generalized way to talk about something being orthogonal. So we have this so far. These are things that you should know now. Dot product equals 0 scalar means that the vectors are orthogonal. Also, 2 vectors being parallel means one vector is a scalar multiple of the other. We'll actually talk about another way to talk about parallel tomorrow as well when we do the cross product. But for now, you can just know 2 vectors are orthogonal if their dot product is 0. Namely, specifically the 0 scalar. A dot product is a scalar. All right. So I have a bunch more examples to do here, but let's actually do one. Let's do one example and wrap up there today because, you know, I'm kind of feeling out of it today anyway. So let's actually, I was like slurring and I did talking a lot slower than I normally would have. But let's actually do this. I'm all right. I'll survive. It's nothing crazy. Okay, so we have here are two vectors. I just want you to find A dot B, and then I want you to find the smallest angle between A and B. And so when it comes to actually finding a dot product, it's actually not so bad. So here we have A dot B. And again, you write the dot. The dot is important because there's going to be other notations, other ways that we want to combine vectors. Dot is important when thinking about a dot product. Important when thinking dot product. Okay. So whenever you see that, it means you're going to take corresponding components and multiply them, and then you're going to add these guys together. So you're going to take, for these three-dimensional vectors, you're going to take A1, B1 plus A2, B2 plus A3, B3. That is the dot product. And in fact, technically you don't have to write this down, but so let's just put that in some that you can actually leave out. And so you'd actually do that. So it'll be 1 times 1 plus 2 times 0 plus 3 times minus 2. So this is end up going to be 1 minus 6. So this is minus 5. That is the dot product of these two vectors. Now, if someone were to ask you, what is the smallest angle between A and B? Well, we would use the fact that we know that A dot B is equal to the magnitude of A, magnitude of B, cosine theta. In other words, this means that our theta is going to be the cosine inverse of, well, our A dot B divided by magnitude of A, magnitude of B. A dot B we just found. That was minus 5. Magnitude of A, magnitude of B. So A is 1, 2, 3. So this is going to the magnitude of 1 squared plus 2 squared plus 3 squared times magnitude of B. 1, 0 minus 2. So it's going to be 1 squared plus 0 squared plus minus 2 squared. So this is going to be the cosine inverse of minus 5 divided by, this would be radical 14. And that'll be radical 5. And that's actually it. Now, I calculated this earlier. This is roughly 2.21 radians. So now, based on the law of cosines, what we discovered before, give me any two vectors in the same space. Of course, they have the same number of dimensions. I can tell you what the angle between them are by using a dot product to help me. So I can use the dot product inside of this, an inverse cosine, and that can help me figure out what the angle between these two vectors are. So we'll wrap up there today. I will leave these examples for you guys to try. And we will pick up with those tomorrow. So today we learned about the dot product. We learned kind of where it came from, why it's important. We need a way to find angles between vectors. We need a way to measure area. We needed a way to measure direction in terms of orthogonality. The questions that I brought up that were important, that we have not yet dealt with, we will deal with them tomorrow when we deal with the cross product. But for now, all you need to know about dot product is the following. What's very important about the dot product, you don't need to know how to actually derive it using the law of cosines or anything, but you do need to know what I put in a box. You need to know what the definition of a dot product is. You can take a dot product of vectors in any dimension. The cross product only works in 3, but the dot product works in any dimensions. As long as the vectors themselves have the same number of components, you can find their dot product. The dot product gives you a scalar that is very useful in finding the angle between the two vectors. So a dot product you can think of as a measure of how two vectors are aligned, right? The important scalar for a dot product is the scalar 0, that is the one that tells you that you are orthogonal or perpendicular. And it's of course important to remember the dot product is a scalar. There's a reason that I put this in red and bolded and all caps and a bunch of exclamations behind it. Okay, so these are the properties of the dot product. Make sure you know those. And everything I put in box here, you should make sure you know. So with that, we'll stop there and I will leave these guys up for you guys to try and we'll pick up with that tomorrow.
Professor?
Yeah?
I'll like to speak to you after class.
Okay, I'll send you the link.
Mm-hmm.
All right. And with that, we are going to end today. So we did a lot of good stuff, a little bit slower and sloppier than I wanted to, but life goes on. I will see you guys tomorrow, actually, but stay safe and I will try those problems. Hopefully the quiz is good and I will see you guys in the next one. Ciao.